Okay, so thank you very much for inviting us today and giving us this opportunity to present the work. In this presentation today, we'll talk about the chronostratigraphic approach that Geoscience Australia developed during the Exploring for the Future program to map the cover. And this work is part of a more ambitious project that aims to map the cover at national scale to provide a geometric basis for resource modeling. All right, so why a chronostratigraphic approach? Well, depending on the type of resources you are targeting, you will need to map different surfaces. And for example, in the East Tennant Creek area, explorers will be interested in the pre-Neoproterozoic rocks for iron oxide copper gold deposits, whereas they will focus on the Cambrian age sediments for phosphate deposits. So to address these different needs and help explore undercover, we have adopted a layered approach to map the geology in space and time. And as a start, because it's a huge area to cover, as a start, we focused on mapping the depth to the base of geological eras because they correspond to clear unconformities and therefore they represent a good starting point to develop a national stratigraphic thickness framework. So how can we map below the cover? Well, given that the cover accounts for about 80% of the continent, we cannot realistically only rely on conventional field mapping and sampling, and instead we need to develop a new approach that involves enhancement and acquisition of multidisciplinary and multi-scale datasets, as well as the development of predictive tools to help us predict what lies under cover, and going from these 2D geological maps to a layered model. But how can we see through the cover? So without going into too much details, because I think you recently ran a webinar on AEM data, the airborne electromagnetic data is a great tool to map geological features under cover. And this is the AusAEM survey that extends across about 2,000 kilometers from east to west. And it was acquired with a 20-kilometer line spacing and supplemented with infill company data. And this data shows the electrical conductivity of the subsurface that varies based on the rock's physical properties. And at first order, I think you already saw those images in the past, you are able to identify the resistive basement in dark blue and conductive sedimentary basins in warmer color. And using the infill data, we can map at a higher resolution, for example, to refine the geometry of paleovalleys or map the water composition variations. Now, if we have a look at one line in more details, you can see lateral and depth variations of the electrical conductivity. And because the flight lines were diverted to intersect locations of drill holes, we were able to correlate these conductivity changes with the stratigraphy from drill holes and from the surface geology. And the pink line here represents the limit of interpretation that goes down to about 200 to 300 meters. So using this data integration approach and with the objective of mapping the cover at continental scale, we conducted a first pass interpretation of the AusAEM 1 survey. And we focused on mapping the major age boundary. And from this interpretation, we were able to reevaluate the spatial extent of sedimentary basins and map the cover. Now, this interpretation was compiled in a new database called the Estimates of Geological and Geophysical Surfaces, EGGS. EGGS is the backbone of the cover modeling work. This platform enables to store depth estimates from various datasets and respect the FAIR principle by making the data findable, accessible, interoperable, and reusable. EGGS is underpinned by other databases at GA. For example, the stratigraphic interpretations that define major age boundaries, such as the overlying and underlying units, are linked to the Australian Stratigraphic Units database. And this allows to maintain consistency and store up-to-date stratigraphic information. But also, it allows to facilitate the update of interpretation with an evolving geological framework. For example, if new dates are published for a given stratigraphic unit, you may need to revise the depth of your major age boundary. So this is a snapshot of the eggs user interface. So there is absolutely nothing exciting about showing you how data entry works in eggs, but here I just want to emphasize the importance of data management in the cover modeling workflow. And we need to collect a significant amount of metadata for each depth estimate to be able to select and filter the preferred depth point. And here that's just an example for the depth interpretation and uncertainty. We have another example for stratigraphic interpretation. And regarding the depth estimates interpreted from geophysical methods, EGGS was designed to maintain the links to the underlying datasets and processing steps. This includes keeping track of the survey specifications, as well as the inversion algorithm and parameters on which the interpretations are based. What does it mean? Well, if you change, for example, the velocity model for a depth conversion of a seismic line, your depth estimates will change as well. So we need to keep track of these changes to allow repeatable science and justify the change of our cover model. So at the moment, EGGS is still in its early stage of development, and as we start to use it a bit more, we will find more features or metadata to add. And down the track, we also plan to add some uncertainty to the depth estimates that would result, for example, from the data processing. So to date, we have over 220,000 points stored in EGGS that you can visualize based on multiple attributes, the depth or the edge boundary names, for example. And here I would like to make two comments as well. So as you can see, it's a very large and very complex data set. And of course, mistakes exist. So if you come across any inconsistencies, we really welcome your feedback, as we want to make sure this data set is as usable as possible. And the second comment, as we know, depth-to-basin modeling is a data-intensive work. And basically, we never have enough data to do it properly. So while including the states and territory data sets will be our main priority in the near future, we also welcome any additional contributions if you think that you will be able to provide new depth estimates with mandatory metadata. Now, going back to the cover modeling workflow, how can we use this data set to build the cover model? So if we extract from EGGS the depth points for a particular surface, for example, here the Mesozoic, we can grid all the points using an interpolation algorithm. And in that case, we will usually get a fairly good result where we have a high density of points, but it will become less reliable away from these points. Now, if we assume that correlations exist between the depth estimates and other geological and geophysical datasets, we can also use a machine learning platform. In that case, you will define your predictive relationship using additional data sets, such as the gravity, the magnetic, distance from outcrop, and you will be able to generate your predictive surface. So you can see here that the results show very similar predictions, at least at regional scale, given that we have a very high density of input depth estimates. But if you look at a smaller scale, you can see more variations in the machine learning model. In that situation here, the platform that we use is called UncoverML, and it was developed in collaboration with the CSIRO Data 61 team and Geoscience Australia, using the National Computational Infrastructure. So as the machine learning approach will help you enhance the prediction where you have sparse data distribution, but more importantly, if you use a probabilistic model, you will also be able to quantify the uncertainties of the predictive surface, which will give you the ability to assess the results in a more objective manner. And as an example here, still for the Mesozoic surface, the green colors on the right indicate that the difference between the model and the input data is less than 10 meters, whereas in red, the error is greater than 200 meters. So this is a work in progress. And so far, using this machine learning approach, we were able to produce the Cenozoic and Mesozoic surfaces with uncertainties. And we are currently in the process of generating the Paleozoic and Neoproterozoic surfaces. However, Given the huge number of depth estimates we were able to compile, we also produced a first pass cover model using a minimum curvature interpolation method. And to further characterize the cover and visualize more easily the depot centers, we also produced the isochore map that reveal the thickness of the Cenozoic, Mesozoic, Paleozoic, and Neoproterozoic sequences. All right, so now we have one more missing piece in our cover model, and that is the composition. So to characterize the cover composition, we completed a seamless solid geology dataset across North Australia. And based on over about 220 quarter-million scale map sheets, about 1,000 drill holes and magnetic data, this work consists of peeling off stratigraphic units layer by layer to reveal the extent and nature of all the rocks. So this dataset enables to predict the spatial distribution of stratigraphic units that can be prospective for minerals, energy, and groundwater, and it can expand exploration opportunities significantly. So this dataset combined with the isochore map that I showed you previously, this layered geology provides key inputs to constrain gravity and magnetic modeling and generate more targeted cover or depth to basin models. Now to conclude the first part of this talk, from the enhancement, acquisition, and interpretation of new large-scale datasets to the development of new tools, we were able to streamline the cover modeling workflow and generate a consistent predictive cover model in a semi-automatic manner. Today, I mainly focused on the depth modeling, but a similar approach can be used to characterize the cover composition using surface data and enhance, for example, the predictive capacity of a geochemical survey. This predictive mapping approach integrates multidisciplinary and multi-scale datasets to assess the resource potential at regional scale. And one example here we have for the pre-Neoproterozoic surface, where only 10% of those prospective rocks outcrop. Our model was able to reveal that about 35% of these rocks lie under a cover that is less than 250 meters thick. So of course, there is no need to say that this model will need to be refined as new data becomes available, but it's a work in progress. I should also now mention that this work is the result of a huge team effort, and behind every single image that you have on this slide, there are multiple teams, about 6 to 8 people for every single team. And I would really like to acknowledge all of my colleagues and thank them for their punctual or continuous input into this work. So that's the end of the first part of this presentation. You may have noticed that the cover model I presented stops at the base of the Neoproterozoic, but there is much more to map below that surface. And now Nadege will zoom into the South Nicholson Basin to have a look at these deeper structures down to the basement. Thank you.
Thank you, Marie-Aude. I'm going to share the screen. Okay. Can you see the screen?
Yes, we can see it.
Okay, thank you. So thank you, Marie-Aude. So I'm going to zoom in now in the South Nicholson Basin, looking at the chronostratigraphic cover model down to the basement. So as Marie-Aude just presented, we have used our first pass interpolated cover model from the surface through the Cenozoic, Mesozoic, Paleozoic, and down to the base of the Neoproterozoic to help us calculate isochore maps to provide the thickness of this major era geological, those major geological units. And as well, this helped us to locate the major depot centers through time. For example, the Mesozoic Carpentaria and Eromanga Basin, highlighted here in yellow, the Paleozoic Wiso and Georgina Basin, and the Neoproterozoic to Paleoproterozoic Beetaloo and South Nicholson Basin here. So all these data have been recently released as part of the EFTF program, and you can download the data points and these first pass interpolated surfaces from our GA website following the link at the bottom here. Now I'm going to zoom in the South Nicholson Basin that is highlighted by this purple polygon, where we have recently acquired deep crustal reflection seismic data to assess the resource potential between two highly prospective regions, the Mount Isa province to the southeast and the MacArthur Basin to the northwest. On this map, the blue line represents the South Nicholson Reflection Seismic Survey, the red line, the Barkley Reflection Seismic Survey, and the black lines, parts of this massive airborne electromagnetic AusAEM 1 survey. So using this newly acquired seismic, we have refined our cover model by integrating with the surface geology, airborne electromagnetic data, boreholes, and gravity and magnetic data, interpreting all these data to refine the major boundaries, geological boundaries, in a 3D domain, which helped us to build a consistent interpretation between the various data sets. On this image, located in this, this image is located in the black outline on the map on the bottom left. Similarly, we have interpreted and integrated in a 3D domain to map the major structure and crustal boundaries from the surface down through the crust. And as you can see in this region, the airborne electromagnetic maximum depth of investigation is around 300 meters deep, which correlates roughly with the base of the Paleozoic to Neoproterozoic Georgina Basin. So to map deeper, we rely mostly on the reflection seismic data integrated with other geophysical data. The interpretation of the South Nicholson seismic data has recently been released as part of the EFTF program by Carr et al., Carson et al., and Fomin et al. And this interpretation revealed the existence of a concealed basin, the Carrara Basin highlighted here, that highlighted by this dashed red line, and it coincides with the gravity law, and it's also best illustrated on this bottom line, the line SN2. This Carrara Basin is a large sag basin up to 8 kilometers deep, and it has been interpreted to include rocks of the Isa superbasin that are highly prospective and host worldwide deposits such as the Mount Isa copper and lead zinc deposits, and also regional base metal deposits. These host rocks are, can be traced through the Carrara subbasin, and you can see how these rocks are buried beneath a thin veneer of the Georgina Basin, but also below Mesoproterozoic South Nicholson group, equivalent of the Roper superbasin highlighted in yellow here. And underlying this Isa superbasin, we have the Calvert superbasin in blue and the Lacquard superbasin in brown overlying the basement. So future stratigraphic drilling of the Carrara subbasin will hopefully confirm this interpretation. Now we have depth converted this interpretation onto the post-stack depth migrated data that provide information down to 50 kilometers deep through the whole crust. This interpretation is really preliminary and ongoing, and it will evolve with the integration of more data, but also with discussion with our collaborators. On this interpretation, the basement is highlighted by this thick black line, and the MOHO by the thin red line. This MOHO is derived both from the combination of passive seismic deployment records and also with this full crust reflection seismic data. These MOHO constraints have been recently published through the EFTF program by Gorbachev et al. And this MOHO constraint will then be stored in our EGGS database. I haven't plotted here the crustal structure boundaries, as this work is in progress and it's in collaboration with Michael Doublier. But as it progresses, we will be happy to share it with you and help to constrain it better with more data and discussions. So together, the MOHO and the basement provide information on crustal thickness variations that can assist in identifying unknown major structures. So we have also started interpreting the newly processed and released Barkley seismic line. And here, this is an example of the interpretation on the Barkley line 1. This interpretation is in progress, and we are combining interpretation with Michael Doublier and Chris Sousby to look at the relationship between the basin and also the crustal structures. So again, this interpretation is very much in progress, and there will be opportunities to share interpretation to validate our ideas with our collaborators. So from this preliminary interpretation, we can produce a preliminary 3D model by stacking all these new surfaces from the base Georgina Basin to the base Roper Basin, the base Isa Basin, and down to the top basements that correlate to the base Lacquard Basins, and also the MOHO. So, and to complement the seismic acquisition, a comprehensive geochronology program was conducted as part of the EFTF program. This enabled us to have more confident regional stratigraphic correlation in the region, and therefore better constraint for the seismic interpretation. So by interest here, I have correlated the basement trends with other data sets that correlate quite well with the Bouguer gravity on the left and the 2D tomography on the right-hand side. This image of the tomography represents a slice through the shallow layers of the crust between 2 and 4 kilometer depth. And it shows a strong negative anomaly here that correlates with the negative gravity, Bouguer gravity anomaly located here. And it helps us also to delineate the Carrara subbasin. All these data also have been published through the EFTF program and through the program, yes. So to conclude, we are integrating legacy data with newly acquired and interpreted multi-scale and multidisciplinary data in a 3D space using a chronostratigraphic framework to provide a consistent 3D interpretation between the various data sets that can then be validated and refined by gravity and magnetic modeling or also using other datasets and methods. Doing this, we provide a regional geological context to assess resource potential at regional scale, but also at a more local scale. For example, here in the South Nicholson Basin, where we are currently building deeper surfaces using a Proterozoic chronostratigraphic framework to provide additional surfaces to the cover model. We could do a similar thing to refine the upper cover by adding key surfaces at geological period levels instead of eras. And doing this, we can use the Paleozoic Centralian chronostratigraphic framework and the Mesozoic Northwest Shelf framework. So then all the new constraints will be uploaded progressively into the X database. And as we compile more data, it will feed into the cover model using machine learning. So all this work, as Marie-Aude said, couldn't have been possible without the cooperation of many teams and the huge effort that has been undertaken. And I apologize if I have missed anybody, but I really want to thank you all. And finally, I also want to acknowledge our external collaborators who have contributed to the outstanding success of the Exploring for the Future program. Thank you. That's it for me.